We're going to continue with Chapter 20 tonight, and we're really going to look at the reasoning of a hypothesis test, and we're going to go through an example. Hypothesis tests follow a carefully structured path divided into 4 sections, and whenever you do a hypothesis test, you will have to do all 4 sections. Now, some problems of your homework will break the sections down for you within the problem, but on a test or the AP test, you will have to do all 4 sections. The first section is the hypotheses. You first state the null hypothesis. This is usually the claim that nothing is different. Again, null meaning nothing. Nothing new, nothing different, nothing out of the ordinary. If we reject the null hypothesis, we find in favor of the alternative hypothesis H sub A. So this is when we reject the null hypothesis, but we still don't know the true parameter. The alternative hypothesis contains the values of the parameter that we would accept if we rejected the null. We really use our alternative hypothesis for the values that we're trying to accept. In a sense, we're trying to disprove our null hypothesis in favor of our new model, and that new model is going to be defined by our alternative hypothesis. Looking at more alternative hypotheses, if we want to see if the percentage of smokers has decreased from 20%, our null hypothesis is that nothing is different. So our null hypothesis would be H sub 0, colon, P equals 0.27. We are assuming that the current model of 27% is what it still is. The alternative hypothesis, we want it to have decreased. So our alternative hypothesis is P is less than 0.27 because we're trying to show that it has decreased. And we're going to do that if we are able to reject our null hypothesis. This is called a one-sided alternative. It's one-sided because we're only looking at the decreased side. We're only interested in it going down. If we were only interested in it increasing, this would also be a one-sided alternative. So essentially, if you use an inequality sign, the alligator mouth, it's a one-sided alternative. If we want to see whether or not people prefer Coke or Pepsi, we would let our null hypothesis be the number of people who prefer Coke. We would assume that since they have 2 options, it would be even. So the proportion of people who prefer Coke is 0.5. The alternative hypothesis in this case is P is not equal to 0.5. We are not interested in them liking Coke more than Pepsi or vice versa. We just want to know, is there a difference? So in this case, we use not equal to. When you have P not equal to the percentage, this is called a two-sided alternative because we don't care if our percentage is actually above or below. The second part of hypothesis testing is the model. Here you have to specify the test you will use to test your parameter of interest, and you have to check your assumptions and conditions. For right now, we're only doing this one test, and it's a hypothesis test about proportions. So it's a one proportion Z test, or a one sample test for a proportion. You must make sure that all the conditions for that model are still met and apply. If the conditions are not met, you cannot proceed with the test. You have to stop and reconsider what you're doing. And all of the conditions that we have to check to do a one proportion Z test are exactly the same as the ones that we had to do for a one proportion Z interval. So we need to check that it's plausible independence, 10%, random, and success fail. So those are the 4 conditions that we would have to check. The third part is the mechanics. The mechanics is where the actual calculations occur. So the ultimate goal of the calculation is to get a p-value. The p-value is the probability that the observed statistic value could occur given your null hypothesis is true. So the way we calculate our p-value is you will first calculate the standard deviation. And note I say standard deviation here and not standard error. And that's because we are going to be able to know what our population parameter is because that's our null hypothesis. So we will calculate the standard deviation. Then we'll be able to calculate our z-score, where our mean will be our null hypothesis and our x value will be our sample proportion. And then finally, we'll use our z-score to find the probability. And that probability is your p-value. If we end up with a small enough p-value, we can then reject the null hypothesis, where we will find in favor of our alternative hypothesis. The fourth part is the conclusion. The conclusion is always a statement about the null hypothesis. You are either stating that we reject the null hypothesis or we fail to reject the null hypothesis. We reject it if we have a small p-value, and we fail to reject it if we have a large p-value. The conclusion should always be stated in context and include your p-value. Every conclusion is worth 3 points. You are going to have to give one of these two statements. You either reject the null or fail to reject the null. You are basing it on the p-value, so the p-value is included in the conclusion, and you explain what that means in the context of the situation. For example, I might say that I reject the null hypothesis because p equals 0.003 is very small. There is strong evidence that more than 50% of all voters favor the amendment. Again, I just made up the context here, just gave an example. This is what a conclusion would look like. So let's go ahead and look at an example. This example is about home field advantage. In 2003, there were 2,429 regular season baseball games. The home team won 1,335 times, or 54.96% of the time. Is this deviation from 50% explained from natural sampling variability, or is this evidence that there is a home field advantage? We're assuming that you have a 50-50 chance of winning at home. In testing the hypothesis, we are asking whether the observed rate of home wins, 54.96%, is so much greater than 50% that it cannot be explained away as just chance variation. We're going to start by stating our null and alternative hypotheses. So our null hypothesis, h sub 0, is p equals 0.5. Our alternative hypothesis is essentially what we're trying to prove, and we're trying to show that there is a home field advantage. So if there's a home field advantage, then our alternative would be that the probability that the home team wins is greater than 0.5. So this was our first step. Our second step is to state what model we're going to use, and we're doing a 1 proportion z-test, and then we have to check all of the conditions that apply. So these conditions are our plausible independence condition, our success-fail condition, 10% condition, and random condition. So I'm going to start with random, and in this particular case, because it's an entire season, we can say that 2003 can be considered a random season out of all of the seasons that they would play. Then when we check the plausible independence and the 10% condition, in a sense I'm going to do this one together because we don't have 10% of the season, we have the whole season, and that's okay. So for the independence, we can say that the 2003 season is independent of all seasons. And then lastly, we have to check our success-fail condition. So the number of successes is equal to n times p, which in this case is 1,335, and that is greater than or equal to 10. And then our failures is n times q, which is 1,094, which is greater than or equal to 10 as well. So this means that our conditions are met. We showed that they were random, independent, and we have our success-fail condition. Our third step is to perform the actual calculations. In this particular case, it's helpful to have your null and alternative hypotheses right in front of you, so I'm going to go ahead and rewrite them. So my null hypothesis, again, is equal to 0.5, and again, my alternative is that it is greater than 0.5. In order to perform the calculations, we want to calculate our p-value. In order to calculate our p-value, we need a z-score. So remember that the equation for a z-score is equal to x minus the mean, and in this case our mean is p divided by our standard deviation. So I need to calculate my standard deviation. So standard deviation is going to be the square root of p times q all over n, and there were 2,429 games. So this gives us a standard deviation of 0.0101. Then we calculate our z-score. So z equals 0.5496 minus 0.5 all divided by 0.0101, and this gives me a z-score of 4.89. Having a z-score of anything above 3 or below -3 should send a red flag that your probability is going to be basically 0. So in this case, the probability that x is greater than 0.5, which is equal to my p-value, is equal to 0. And there are 6 zeros there, and then 5. And this is basically 0. What this p-value means is that there is essentially a 0% chance that the home team would win 54.96% of the time if there were no home field advantage. So finally, we can draw a conclusion then about home field advantage. And our conclusion is going to be, with a p-value of 0.0001%, because I rounded, we reject the null hypothesis. Thus, there is strong evidence the true proportion of home team wins is more than 50%, which means that there is a home field advantage. So this is an example of a hypothesis test. You state your null and alternative hypotheses. You state what test you're using, check the conditions that verify you can use that test, and then perform the actual calculations to calculate a p-value. Then you base your conclusion off of your p-value. And note that every conclusion gives your p-value, states that you reject the null hypothesis or fail to reject the null hypothesis, and then you put it all in context of what it actually means. And we've done all of that here. That is it for tonight. I hope you guys have a great night, and I will see you tomorrow.